want to welcome you to another statistical topic. Of course, we actually starting chapter 7 today, so which is going to go from today to Friday. But the knowledge of chapter 6, chapter 5 and 6, highly needed in chapter 7. And of course, because of that, I'm going to, walk you through some stuff. If you look at the outline, okay, I'm going to talk about linear combination of chi-squared. I'm going to talk about the beta distribution and its property because the beta distribution that we started the other time is also formed from the ratio of two independent gamma. Okay, so which is more or less like a function of a random when it was derived as a function of a random variable. Then I'm going to talk about the functions of random variable in general. Okay, so this is the story I started the continuous probability type distribution. Started from the exponential uniform to normal to exponential, but we started seeing relationship all the way from exponential. Okay, we realized that the gamma distribution was a generalization of exponential distribution. So which means, in a way, gamma distribution can be derived from exponential distribution. And from gamma distribution that I gave you the other time, I remember when I was giving a gamma distribution, okay, if X follows gamma, with parameter alpha beta, okay, f of x is equal to x raised to power this raised to power this divided by this, beta raised to power alpha, x greater than 0, alpha greater than 0, beta greater than 0. But let me tell you the situation where I actually if I let our beta to be equal to 2, and I let alpha to be equal to v over 2, okay, where v is degree of freedom, okay, okay, then a new distribution is formed. And that very distribution was actually called chi-square distribution. Okay, so if I want to rewrite this gamma now, okay, when I plug in beta equal to that, alpha equal to that, then of course, I'm basically going to have a chi-square distribution. So now this is basically going to be this guy exponential raised power x over 2, then divided by the gamma v over 2 raised to power v over 2. When you take a look at this now, the only random variable in a chi-square distribution is, the only parameter in a chi-square distribution is v, degree of freedom v. Take a look at that. So which means the chi-square distribution was actually derived from gamma distribution. So take a look at that. Now, do you know that the story doesn't end in chi-square distribution? Do you know another brand new probability distribution can also be derived from chi-square? Now, that is what I'm presenting now, where I'm actually talking about a linear combination of a chi-square random variable. But let me tell you this. When I square, well, for instance, if I have a random variable that is a chi-squared, okay? If I have a random variable, okay, that is a chi-squared, okay? And we have another way to arrive at a chi-square. Let me tell you this. There's so many ways to arrive at a chi-square. The first way to arrive at a chi-square is to pass through a gamma distribution. The moment you set your alpha to be v over 2, and you set your beta to be 2. Then you're going to get a chi-square from gamma. Another way to get a chi-square is just like you want to get to this venue now of the lecture, and somebody can say, okay, if I want to get here, somebody can decide to take the other side to call. Somebody can say, okay, I'm going to pass, maybe I'm going to go through the other side. But in the end, I know some of you, that you are here today, that you are in this class now, you didn't come from the same destination. You must have passed through different destinations. So what I'm trying to talk about is one way to get to chi-square is passing through gamma. But another way to get a chi-square is when I have a random variable z that follow normal distribution with this. This is a standardized normal distribution. The f of z is basically going to be 1 over square root of 2 pi exponential raised power minus half z squared. Okay, you know where z is basically going to lie between negative infinity and infinity. This is a standard normal distribution. Do you know that if y equal to z squared, if I square z, and what is z? Z follows standard normal distribution. When I square z, that will give me a chi-square. That is another way to get chi-square. I'm going to say that again. The first way to get a chi-square is passing through gamma distribution. When you set alpha equal to v over 2, when you set beta equal to 2, the PDF of a gamma distribution become the PDF of chi-square distribution. But you know another way to get to chi-square is when I have a random variable z that follow a normal distribution with a mean of 0 variance 1. Then when I square z, of course, when I square a variable, it is not the same variable anymore. The state space will be different. Not only that, the probability distribution will be different. So what I'm trying to say now, if y follows this, if y equal to z squared, okay, the y now, which is the square of z, is basically chi-squared. It's chi-squared. Now, what am I talking about? Take a look at this. If I have x1, x2, up to xn, particularly, look at the theorem here. Look at this particular theorem here. Do you see that theorem? For those of you online, what I mean, when you take a look at this theorem that I circle now, for those of you online, that is talking about z follow standard normal distribution, just like what I said. The square of z will follow chi-squared with degree of freedom 1. But what of the situation where I want to talk about the combination of that now? Take a look at this. If I have this guy now, if I have y equals z1 squared plus z2 squared, and zi follow normal, which means 0, 1, this is still going to be a chi-squared, but it's basically going to follow chi-squared with degree of freedom 2, because 1, 2. If I now want to have it in n times, if I now generalize, maybe I have a z1 squared, z2 squared, until I get a z squared n, then this follow chi-squared with the degree of freedom n. Any question? So the numbers of degree of freedom depends on the numbers of variable you are squaring. And what is the z? What does z equal to? Don't forget, z is this guy here. Any question on what I'm displaying now? Any question? Okay, now, if you guys are good, then I'm going to go to the next slide. Now, the next slide, I want to focus on the beta distribution. I started on Monday. The beta distribution is the most versatile distribution in statistical analysis because of its flexibility. The beta distribution is a distribution that we use to model proportions, percentages, if a random variable lies between 0 and 1. What do I mean? Greater than 0, but less than 1. Now, you know, if x follow beta with parameter alpha beta, I told you the other time, the beta distribution will enable you to know what is the click rate of customers that visit your website. What is the click rate that they're going to watch your adverts? What about the conversion power? Like in terms of purchase, it is not all customers that visit your website that actually purchase your product in the end. What if you want to find, what is the probability that more than 50% of customers that visited my website, they're basically going to purchase my products? They're going to use a beta distribution. What is the probability that a president in power, what is the probability that it's actually going to secure a second term? Because it could secure second time or not. The probability will lies between 0 and 1. Does that make sense? We're going to use a beta distribution for that. Now, if I want to talk about beta distribution, when let's follow that, I'm actually going to have x raised to power this, 1 minus x raised to power this, divided by b of alpha beta, and the range of x is from 0 to 1. X is a random variable here, is a proportion. Does that make sense? It's a percentage. Okay, when I have this guy now, okay, for you to be able to understand the properties of a beta distribution, that you need to understand, you need to first of all understand what we mean by beta function. Okay, now we want to consider beta function now. Okay, you need the knowledge of beta function for you to be able to understand beta distribution. Just like the way we have in the gamma function, you need the idea of a gamma function to understand the gamma distribution. You remember we have integral definition of a gamma function. We have a non-integral. We also have integral definition for beta, okay, which is going to be b alpha beta equal 0 to 1, x raised to power alpha minus 1, 1 minus x raised to power beta minus 1 dx. This is integral definition. We call this guy now integral definition of a beta function. It has to be from 0 to 1. If it is not from 0 to 1, it doesn't work. Okay, now what is the non-integral definition now? The non-integral definition is basically going to be gamma alpha, gamma beta divided by gamma alpha plus beta. This is a non-integral definition now. Non-integral definition. And you know what? Integral definition equal to non-integral definition. If I want to rewrite this guy now, I have a gamma alpha, gamma beta, or gamma alpha plus beta. Another way to write that, because take note, the gamma k is the same thing as k minus 1 factorial. Gamma k is the same thing as k minus 1 factorial. If I want to rewrite this guy now, you know what I'm going to do? I'm basically going to write b alpha comma beta equal, instead of gamma alpha, I'm going to have a alpha minus 1 factorial, beta minus 1 factorial, alpha plus beta minus 1 factorial. Take a look at that. That's another way to present all this using the fact that gamma k equal to that. Any question? Math is easy, right? Okay, now I'm going to use this knowledge now to derive what I call the CDF of a beta distribution. Let me tell you, the CDF of a beta distribution is incomplete. Just like that of the gamma distribution. You realize the other time, right? When you're solving a problem with gamma, we were using a statistical table, right? Okay, now let us see now. We want to the person online, can the person online still see the board? The person online, can the person online still see the board? Is that person still online?
Yes, I can see the board.
Thank you so much. If you're not seeing the board, you let me know. Thank you for answering that. Okay, now, and you know, if you want to ask question, the person online, please, you can ask me question, okay? You can talk if you need any clarification. Now, I want to derive the CDF, which I call the cumulative, the probability of x less or equal to that we call this guy an uppercase. I want to derive that for the beta distribution. So if I want to do that for the beta distribution, it means basically I want to do 0 to x. Okay, what is the beta distribution? T raised to power alpha, 1 minus t raised to t raised to power alpha minus 1, this dt divided by b alpha beta. You know, I said if I want to go from 0 to x, then I'm not going to be talking about x anymore. I'm just going to use something else. Does that make sense? Now, do you know that if I have something like this, you know, this is going to be an incomplete. And, you know, and that is the reason if you take a look at this guy, and I said the incomplete beta function. So this guy here, the numerator, basically going to be incomplete. Do you know what we normally write in statistical analysis? But the only way it can be, for instance, if this is 1, the whole thing is going to be 1. Why? Let's see. Using the beta function here, take a look at this. If this is 1, then the numerator is also going to be b of alpha comma beta. And the b, they will cancel out, they're going to be 1, right? That is if x is 1. But this time around, we're not going to 1. We actually want to truncate. Does that make sense? At a particular point, x, and that very x is less than 1, that's going to be incomplete. Now, because of that, I'm actually going to write this guy now. Okay, if I want to rewrite the whole thing now, this is what I'm actually going to do. If I want to rewrite the whole thing, this guy, I'm going to say b x alpha comma beta, then divided by this. Now, what am I talking about? This guy, this is another way to write it. It's an incomplete. Anywhere in the world, the probability of x less or equal to that is this guy here. This is a cumulative distribution for beta distribution. Okay, now, so another way to write that, the whole of this guy is the same thing as ix, you know, is written as ix alpha beta. The whole of the ratio. Incomplete at a point x. Look at that. Incomplete at a point x. If x equal to 1, like for instance, if I do I1 alpha beta, the I1 alpha beta is going to be equal to 1. When you plug in 1, they're gonna cancel out. Okay, so take a look at that. That's what I'm doing here. Look at that b. Do you see b when you plug in 1? When you plug in 1, it's basically going to be that. Well, if you plug in 0, when I go from 0 to 0, what happen? There's no distance. That would be 0. That is what you see in A. So you can ask to prove that property. All we just need to do, just plug in the values of x. Now take a look at C. I want you to take a look at C now, where we got our, incomplete x. Alpha comma beta equal to that. What do they mean? I'm gonna tell you now. You're gonna see what it means. Now, this is the situation. I'm talking about C now. Okay, I incomplete at x, alpha comma, beta, I, 1 minus x, beta, comma, alpha. Now, what is this guy here? So this guy here is bx alpha beta divided by b alpha, comma, beta. Now, this guy here is when I have 1 minus x, okay, beta alpha divided by this guy here. Now, what is happening? What is the difference between this and this? You're going to see now. Okay, if this guy, bx alpha beta, is 0 to x, t raised to power alpha minus 1, 1 minus t raised to power beta minus 1 dt, then the other one, okay, that is this guy, b into 1 minus x beta alpha. It means I'm actually going to have, where I got a t now, what I'm going to have is going to be beta. It's going to be beta minus 1, 1 minus t raised to power alpha minus 1 dt. Oh, give me 1 second. That will be to 1 minus x. Now, do you know that mathematically speaking, the two of them are the same? I mean, this guy is the same thing with that guy. The only difference now, I switch this for this. When I switch this for this, I'm no longer talking about from 0 to x, but from 0 to 1 minus x. Okay. Now, leaving that property now, I'm going to go to the mean. How do we get the mean? I think I derived the mean the other time. Okay. And of course, you can follow the same way to derive the variance. Okay. So I'm not going to talk about that today. So you can be given the beta distribution and we ask you to show that the mean equal to that and the variance equal to that. Okay. Now let's, so which is that? Look at it, example 6.31. Prove that expected value of x equal to alpha over alpha plus beta. So if you basically, let me remind you, I'm going to remind you now. I'm going to remind you now. Okay. Now, if I want to find expected value of x, it's going to be 0 to 1 x f of x dx. So you actually are going to have 0 to 1 x, and this is x raised to the power alpha minus 1, 1 minus x raised to the power beta minus 1, b of alpha beta dx. So when you follow what we did the other time, okay, you're basically going to, when you're going to have at the end of the day, is basically going to be this guy. And don't forget, if you want to find the variance of x, you need the expected value of x squared minus expected value of x or squared. So which means you need to expected value of x squared is going to be 0 to 1, x squared, x raised to the power alpha minus 1, 1 minus x raised to the power beta minus 1, divided by b of alpha comma beta dx. Okay, you're going to figure out this out, then, you're going to do that. Then you're basically going to derive the variance of the distribution. Okay. Now, can we have an example here? If I take a look at the uniform distribution on 0, 1. Now, let me tell you this. Do you know there's a connection between uniform distribution and beta distribution? That was the reason why I told you the other time, the most versatile distribution, the most flexible distribution in statistics is beta. And that's why beta distribution is being used in, mostly in statistical analysis. Now, I'm going to show you something now. You're going to see something now. You're going to see a connection between the uniform distribution and a beta distribution. Now, I remember the other time when we next follow unif with a parameter AB, the f of x is 1 over b minus a, right? What of the situation where we got 0, 1, where the minimum is 0 and the maximum is 1, if you plug that in here, the uniform give you 1, right? The f of s is going to give you 1. Now let's do something now. In a beta distribution, if a beta if x follow beta distribution with the parameter that f of s is going to be equal to this guy, 1 minus x raised to power that guy, b of alpha beta. Now you know what I want to do now. Let me also set this parameter now, okay, to 1 and 1. If I set the parameter in the beta distribution to 1 and 1, let's see what is going to happen. To 1 and 1, the anything raised to power 0, that's going to be 1, right? 1 divided by b, 1, 1, right? Okay, and what is b, 1, 1? Okay, you remember that b of alpha beta is gamma alpha, gamma beta over gamma alpha plus beta, the non-integral definition of a beta function. If I want to use that here, it means my b1, 1 is gamma 1 over gamma 2. What is gamma 1? I told you gamma k is k minus 1 factorial. So this is going to be 1 minus 1 factorial, 1 minus, so I'm actually going to have a 0 factorial divided by 1 factorial, which is basically going to be 1. So therefore I'm going to have 1 divided by 1, that will be 1. Then it means where uniform distribution has parameter 0, 1, where the minimum is 0, the maximum is 1, is basically going to give the same distribution when the alpha and the beta in a beta distribution is 1 and 1. So which means if a beta distribution want to become a uniform distribution, the two parameters have to be set to 1. That's what I mean. Now, when you have 1 and 1, in that situation, the mean of the uniform becomes the mean of the beta. The variance of the uniform becomes the variance of the beta. Let's see. What does it mean in a uniform? That is a plus b over 2, right? Now, a plus b over 2. Now, in the case of, when I say a plus b over 2, so 0 plus 1 over 2, that would be 1 over 2 for uniform. What about for beta? Where alpha equal to 1, beta equal to 1 is also going to be 1 over 2. Because the mean of a beta is alpha over alpha plus beta, which is going to be 1 over 2. Then the variance is going to be that. Any question? Whether online or in person, any question? Any question? Okay, now we want to go into an example now of a beta distribution. The beta distribution has considerable application in reliability problems in which the basic random variable is a proportion. I told you, proportion. No, lie between 0 and 1, right? That's a probability. Okay, as in the practical scenario illustrated in exercise 6.50 on page 206, of the textbook that we're using. In that regard, consider review exercise 3.73 on blah, blah, blah. Now they're talking about impurities in batches of a product, of a chemical process. Let me reflect a serious problem. The quality control officer in this particular company want to ensure that whatever they produce conform to specified standard. Okay, of course, they actually targeting purity, right? Pure, right? And the purity of the chemical. Therefore, impurity becomes an issue. Okay, when they produce a chemical, it's either it is pure or not. Okay, now we want to figure out what is the proportion of pure, or the proportion of impurity. Okay, we should know, the proportion of impurity cannot be 0% and cannot be 100%. You know that if it is 0%, it means there's everything that they produce is pure. That is never going to be possible. We live in a stochastic world. You understand what I mean? No machine is 100% efficient, and there's no, you cannot also have a situation whereby 100% of what you produce is impurity, but it's going to lie in between. Now, based on what you have now, it is know that the proportion of impurities. Now, the random variable here now is the proportion of impurity. Why do we want to use a beta? Because a beta distribution can actually be used to model a random variable that is in the interval 0, 1. And proportion is in the interval 0, 1. Now you are giving this guy now. You are giving this guy now. Which means there's going to be a probability function for impurity. This is what the engineer or the mathematician actually derived, where the impurity lie between 0, 1. Okay, take a look at that. Okay, now they said verify that the above is a valid density function. If you want to verify that, what they want you to verify that is going to be equal to 1. Does that make sense? If it is equal to 1, because if the total area under a curve is not equal to 1, then you cannot use. Then that is not a probability. Then it's a function. Okay. Now, any question on that, on how to verify that? Any question on how to verify that? Okay, if you want to verify, you put this guy here now. Use this, and the final result should be 1. Any question? You're good, right? Okay, now look at question 2. What is the probability that a batch is considered not acceptable? Okay, y greater than 0.6. Oh, when we count our product and we realize 60% of them, in fact, more than 60% of them are impure, what is going to happen? They are not going to accept that because the majority of what you produce are impure. Now, what do I want to do? I want to find the probability of y greater than 0.6, which means I'm going to go from 0.6 to 1, greater than. Then I'm going to use the function 10, 1 minus that, the y. Any question? That would be super easy to do. Okay, now the next thing, what are the properties of alpha and beta? This is where I want you to see now. For instance, what is the values of alpha? What is the values of beta? Based on this that I'm giving, if I really want to know that, I need you to pay attention now. Okay, I need you to pay attention now. If you really want to know that, what I will advise you should do, write the standard beta distribution. This is the standard beta distribution, right? You want to compare this guy with this guy. But you need to rewrite this guy. If I want to rewrite the given question, I'm basically going to have, now see the way I'm going to rewrite that now. Can somebody see that? There is no y here, right? But there is y. But the y is carrying power of 0. That's not, it's not appearing. Okay, now take a look at that. And this is 1 over 10. Okay, I want to figure out what is my alpha, what is my beta. Now, you know what you're going to do? Equate this guy to this guy. There's an equation, right? You're just going to do alpha minus 1 equal to 0. Solve that. What is my alpha? 1. Equate this guy to this guy. What are you going to have now? Beta minus 1 equal to 9. What is my beta? 10. I'm done. The parameters is is alpha equal to 1 and beta equal to 10. Any question? Go ahead. Y raised to power that, 1 minus y raised to power that. Check what we've written. You get it now, right? Good job. Now you can see now, and the moment you get your alpha and beta, it will be very easy for you to answer question D. What does it mean? You just plug that in, right? Because the mean is alpha over alpha. Go ahead. Yeah, you can say that again. Not necessarily, but you can also check that. Let's see. That's a good one. I understand what you mean. That's a good one. You know, somebody in class, an intelligent person in class, all of you are smart anyway. Okay, now say, can we just like prove to the world now that beta 110 is basically 1 over 10? Yes. Now we're going to do this. Let's see. Gamma 1, gamma 10, gamma 11, right? Okay, this is going to be 0 factorial, 9 factorial, 10 factorial, right? Does that make sense? Oh, come see something here now. That is going to be 1 over 10. That makes sense, right? If you prove that, then that you validate that. Okay, I know what I'm doing. That's a good one. Okay, now do you know with that you can also get the variance? All what you just need to do is to plug in what you have. The moment you are able to identify correctly your alpha and beta, then the mean and the variance is not going to be any issue. Does that make sense? Now I want to go to new chapter. You know, this new chapter is what we're going to do today and what we're going to do on Friday. But let me tell you this. Knowledge of calculus and algebra is needed in this new chapter that we call the function of random variable. I want to welcome you to chapter 7. What we do here, is if a random variable follow a particular distribution, and I say, okay, what if I square that random variable? Or what if I had one? Or what if I manipulate that random variable in such a way it is no longer original one? Then what is the distribution for that? Because if this guy is black, the way you are seeing this guy now, I don't have a color white, or I don't have a different color. Okay, maybe I'm going to do this now. Between this guy and this guy. This guy follow a particular distribution. Engineer now decided to manipulate and do something to get this guy. Are they the same? Are they the same? No, they are not the same. Then we don't expect their distribution to be the same. We don't expect the probability distribution associated with them to be the same. Does that make sense? Now I'm going to talk about the impurity now, example that we used the other time. We're talking about impurity of a chemical, right? If you decide to talk about, when I do this to the chemical, it's no longer the original chemical, okay? The distribution I was using before, there's possibility. They could be different. Now, because of that, we need the knowledge. It's just like you have a random variable follow standard normal distribution. You now square that. Oh, when I square that, it's no longer going to be a standard normal distribution, but it's going to be a chi-square. How do we show mathematically? You know, the other time I just gave you the information. It's just like somebody say, okay, you know what? Maybe somebody come to me and say, do you know your mom is not your mother? Okay, prove it to me. That's what we want to do now. Or do you know University of Minnesota is the best in the Midwest? Okay, prove it to me. That's what we want to do now. Does that make sense? Okay, now suppose that X. Now, if we want to, if we're doing this, we can do that for both discrete and continuous. Does that make sense? Okay, now suppose that S is a discrete random variable with a probability distribution of f of x. And let's now see X follow a discrete type. We are not having a new variable Y, but that variable Y is a function of X. That's how you see y equal to u of s. And that would be a one-to-one transformation. Oh, I want to go from x. I want to go to y. Does that make sense? If I want to go from x to y, I'm no longer going to be talking about, I can't use distribution of x for y. That of y has to be derived. Now, let me give you an example. Let x be a geometric random variable with a probability distribution given like that. I told f of s equal to 3 over 4, 1 over 4 is by x minus 1. Don't forget, we use a geometric distribution when we're trying to like figuring out how many failures am I going to have before I record the false sources. Does that make sense? Now, the question now is, if x follow geometric, we know the probability distribution. We now want to find the probability distribution of a random variable y that is equal to the square of x. Does that make sense to you, right? Okay. Now, how are we going to do that? Then you need to use an inverse function. You know, if y equal to s squared, solve for x, like express x in terms of y. What will that give you? You're actually going to get two different results. Why two different results? You know, you have s squared could be negative. It can be s can be square root of y, and can also be square root of negative y. Oh, did I actually put that here? Okay. Now, s can be square root of y. It can be square root of negative y. But at times we are working with quadratic. One is positive, one is negative. Particularly, we are talking about something that cannot be negative. I will only go with the positive result. Now, s equal to square root of y. You know what I'm going to do now? I will now plug in wherever I see x. In the conventional equation, I'm going to plug in square root of y. But when I plug in square root of y, I can no longer use the original state space. Original state space was x start from 1 to 3. But now I'm working with y. And what is y? Y equal to square of s. My state space will be squared as well. That's why I got 1 for now. Any question on that? That's super easy, right? Okay. It's super easy when we're working with discrete. And when we're working with one-to-one. Now, this theorem, how many more minutes do I have? Like 5 more minutes or 10? Oh, I think 10. Oh, 10. I used to stop at 110. Oh, it's true. 1220 to 110. I got 5 more minutes. Now, the one I'm presenting now in this theorem, we have a bivariate, x1, x2, and we want to have a new set of variable, y1, y2, but y1 is a function of x1, x2, and y2 is also a function of x1, x2. This is going to be a 2 to 2. Okay. Now, if I want to do that, just like what I did the other time, I need to solve for x1. I need to solve for x2. Then I'm going to plug that in. Now, let's take a look at that. In the example right here, let s1, s2 be independent. Take a look at that. They're going to tell us the distribution. They said x1 follow Poisson. X2 also follow Poisson. The first one with mu1, the second one with mu2. Now, but we want to find the distribution of the sum. The distribution of the sum of the variables. X1 follow Poisson with the parameter mu1. X2 follow Poisson with the parameter mu2. Then I now define a new random variable y, which is the combination of, which is adding x1 to x2. You know what I'm going to do first? I will first get the joint distribution, like multiplying the two PMF. You see what I'm doing? F of x1, s2, because they told us x1 and s2 are independent. I'm going to multiply them. Can you see that? When I multiply them and simplify, I got that. That's going to be G11, GY1, GY2. But what do I need? I only need Y1. but I have a y2 as part of this. What am I going to do? Oh my God, do you remember what we used to do when you have a joint and we're interested in the marginal for y1? What are you going to do to discrete? You're going to sum that over the range of the variable you are not interested in. Do you remember that? Because when I have two variables, we cannot go from two variables to one. We can only go from two variables to two variables, even though they gave us one variable. But in the end, we're actually going to factor out the one we're not interested in. If you take a look at this guy now, and I'm interested in GY1, I'm interested in SY1, oh my God, look at that. That is what I'm going to do. I'm actually going to sum that out even the one I'm not interested in. At the end of the day, I have my results. I'm going to stop here today. I only have 3 more slides, and I will have this. I'm going to start from here on Friday. You know what we're doing now? We're doing that of the discrete. But the tough one, let me prepare your mind. But I'm not going to scare you, but I'm going to simplify that for you. Is when we are working with a continuous one that involves integration. But don't be scared. I'm going to walk it through. So the one I've just showed you today is how do we go from a discrete to discrete? One example, from one variable to one variable, two variables to two. Even though they said y1, you still need to go from 2 to 2, and you just factor out the one you're not interested in. Any question? Any question? Okay, you know, in your makeup, initially I realized that all the students missed the same question. I was like, what's going on here? Is there any, you know, but after my investigation, I realized that the answer key that I provided for a question was wrong. So I'm actually going to regrade that. And of course, your grade is going to change. Does that make sense? Okay, be sure you stay safe and have a lovely day. See you on Friday.